This is a lesson on buffering capacity. Buffering capacity has to do with how well your buffered solution can absorb either an acid or a base. Buffering capacity depends upon having a large concentration of both weak acid and its conjugate base. In a 1-to-1 ratio. This will give you the optimal buffer. Higher concentrations, if you have more concentration of the acid or the base, that will allow more acid or base, strong acid or strong base, to be added to your solution without using up all of the conjugate acid or the weak base and getting to a regular adding an acid or base to a neutral solution. The 1-to-1 ratio allows both the acid or the base to be added equally. That means you're centered in the buffered solution area. You're centered in the buffered area. That means you're equally far away from using up all the acid. You're also equally far enough away from using up all the conjugate base. A useful equation for these buffered solutions, which is probably the only time I would use it, is the Hasselbeck-Henderson equation. pH equals pK, the negative log of the hydronium ion, equals the negative log of the Ka, plus the regular log of the concentration of the conjugate base over the concentration of the weak acid. This is upside down from your normal solutions, and the reason is you're solving for the pH. If you're looking for the ratio, then you have the ratio here of conjugate base of weak acid, which is a lot of questions they're asking for. If you're trying to find out what your pH, if you know your weak base, Ka, you can center it on that. So it's very useful for doing your calculations. An example without all the math, if you add 0.01 molar strong acid HCl to 5 molar buffered solution of any sort, it will change the pH by only 0.0017 parts. Same thing would work if you had a base, strong base. You had 0.01 molar base, it would be the same thing. But it changes that much, 0.1% basically. But if you add the same concentration of acid, HCl, or strong base, to 0.05 molar buffered solution, notice this is much weaker and above, it will change the pH by 0.18. Well, that's not very much still. However, it is much more than that. Now, 0.5 molar solution, buffered solution means you have 5 molar buffered solution means you have 5 molar acid, weak acid, and 5 molar of its conjugate base. The 0.05 molar buffered solution means you have 0.05 molar of the weak acid and 0.05 molar of the conjugate base to it. So if you're going to choose, or if you have a choice, choosing the best buffered solution, buffer components from a list, what you want is to select one that has the buffered pH of what you're searching for equal to the pKa. So the negative log of the hydronium acid that you're looking for, the pH, must equal the negative log of the Ka. Now there are other math calculations that you can do it. Oftentimes they try to find out what ratio of the conjugate base to the weak acid is. They ask you for that, and it'll be like a 1 to 2, a 1 to 1, which would be a 1, and then you plug that into the Henderson-Hasselhoff. I call it the Henderson-Hasselhoff. It's not Hasselhoff. If you're looking for a 2 to 1 ratio, then you put 2 in here and do the log. That concludes this lesson on buffering capacity.